Hi Algebra 2 students, these are the video solutions for your in-class Chapter 8 exam review, and this is going to cover sections 8.1 through 8.6, so all of the material that we've covered involving rational functions in Chapter 8. So the first section that we covered in this unit was section 8.1, and that dealt with inverse variation relationships. So the first question on your review guide asks, why is the inverse variation equation an example of a rational function? So if you think about inverse variation, you're always using this equation, y equals k over x, where k is just some constant. So for instance, k could be something like 1 or 2, where you would have y equals 1 over x, and that's actually our parent rational function. That's the one that we first used to graph and analyze our vertical asymptotes and our horizontal asymptotes. And so that's why our inverse work is looped in with our rational function work, because we have a constant divided by a linear term, and that gives rise to both the inverse nature of how x and y relate, and it also gives rise to the basic graphs that we've worked with. So we're going to go ahead and do some calculations with that inverse variation equation. In problem number 2, it says the variables x and y vary inversely with one another. So as soon as I see that statement, I know I'm using this equation up here. When x is equal to 2, y is equal to 25. So first it says solve for the constant of variation. So what that means is I want to set up my equation, and then I want to solve for k. So I'm given x is 2, y is 25. So I'm going to go ahead and plug those in. 25 equals k over 2. And then in order to solve for k, I'm just going to multiply both sides by 2. So my k value is equal to 50. Once I solve for k, I want to go ahead and plug it back into the equation. That way I have it for use with any other predictions I'm going to do in the future. So then I can tackle part B. When x is 10, solve for y. So I'm just going to take this equation here and plug in 10 for x. So I'll have y is equal to 50 over 10. So my y value is going to be 5. And then it says when y is 100, solve for x. So instead of plugging in for x this time, still using this equation up here, I'm going to plug in for y. So I will have 100 equals 50, oops, not 500, 50 over x. And so then in order to solve for x, I'm going to multiply both sides by x. So that's going to give me the equation 100x is equal to 50. So then I can divide both sides by 100, and I'll have 50 over 100, which is 1/2, or if I want it in decimal form, 0.5. So with these kinds of problems, I want to solve for k. Once I have k, I can predict an x given a y, or a y given an x. Number 3 is going to be an application problem for inverse variation. So it says, Kelly rides her bicycle to work at the Crazy Cart amusement park over the summers. When she rides at 10 miles per hour, oh, it's scrolling down, 10 miles per hour, it takes her 30 minutes to get to work. Assume that time to commute to work varies inversely with speed. If she increases her speed to 12 miles per hour, how long will it take for her to get to work? So the really important information in this problem is in this statement here. The time to commute to work varies inversely with speed. So I want to set up an inverse equation where I say time varies inversely with speed. That's just my inverse variation equation where I substituted in time for y and speed for x. So then I have an x and a y I can get started with in order to solve for k. So when she's cycling at 10 miles per hour, it takes her 30 minutes. So I'm going to plug 30 minutes in for time, and I'm going to plug 10 miles an hour in for speed. So then I can solve for my constant by multiplying both sides here, and I will have k is equal to 300. Now, usually it's a good idea to translate things into the units that you're working with. So this k of 300 would work okay, but I think it's actually going to be a better idea if we say that 30 minutes is equal to 0.5 hours. That way we keep all of our information in hours since the time values are in miles per hour with the speed. So let me back this up here, and I'm going to get rid of that 30 over on this side, and I'm instead going to set it equal to 0.5, which is going to give me an easier constant to work with. So my k this time will be 10 times 0.5, which is equal to 5. So then when I have that value, I can say, okay, my time is equal to 5 over my speed. And that's going to be the equation I can use for predictions. So now it says I'm going to increase the speed to 12 miles per hour. So cycling a little bit faster. And that's my speed, so I'm going to plug that in for time. I'm going to plug that in for my speed to solve for time. So I'll have time is equal to 5 over 12. And so the time value that I'll get out when I divide there, I can either report it as 5/12 if I wanted to for my time, or I can report it as a decimal value. And so in this case, that would be 0.42 hours. And if I wanted to multiply that by 60, I would end up with 25 minutes. So either one is fine as far as how you want to work with time values, and working with the original k value of 300 would have gotten you the same answer as well. So that's our inverse variation. You're always just plugging two values in for y and x, solving for k, and then making a prediction about the remaining variable. Number 4 asks us, which of the following tables represents inverse variation? Which one represents direct variation? Identifying the corresponding k values for each. So it is a good thing to remember that if you are working with inverse variation, then you're using the inverse variation equation, which is y is equal to k over x. If you are working with direct variation, you're working with this equation instead, y equals k times x. So with direct relationships, as x goes up, y also goes up. With inverse variation, as x goes up, y is going down. So once you have those equations in mind, you can identify how you would solve for k in each scenario. So here, in order to solve for k, I would multiply x over to the other side. So I would have k equals x times y. In my direct variation, in order to get k by itself, I need to divide it over to the other side. So I would take y and divide it by x. Now, if I take a look at these two tables, I want to monitor what's going on with the trends. So for this first table, let's call this table A, my x values appear to be increasing, and then my y values also appear to be increasing. So this looks like a direct relationship, because as one thing is going up, so is the other thing that's involved. So what I need to check is if I think it's direct, if I divide each of my y's by each of my x's, does that relationship hold constant? So here, y over x is 3, y over x also 3 here, y over x is also 3 here. So my relationship would be y equals 3x, because the k value is 3. So that one is direct. And remember, we can't just assume it's direct if they're both going up or both going down. We do have to check that constant value at each step. Then for table B, right here, it looks like my x values are increasing, so they're going up, but then my y values are decreasing, they're going down. So since there is an opposite relationship, it appears to be inverse. And so I want to check my k value by multiplying my x's times my y's. So here, x times y is 18. X times y here, also 18. X times y here, also 18. So this is going to be an inverse relationship where my constant is 18. So I have this equation here. This is inverse. So that is it for our inverse variation work. After this, we get into our graphs of rational functions. So this is our section 8.2 material. First up, we want to start by graphing this function, y equals 4 over x. So it is up to you how you want to pick your points to graph a function. I usually like to pick my values so that I get some that are positive, some that are negative, or if I have a vertical asymptote, some that are to the left of that value, some that are to the right. So you want to give yourself a table. Now I know looking at this function, I can't plug in 0 because x equals 0 is my vertical asymptote. I can't try to divide by 0. So I like to put that in the middle of my table. And then I like to pick some values that are below 0 and some values that are above 0. So above 0, let's pick 2 and 1. And then below 0, let's pick -1 and -2. So if I plug 2 in, I'm going to get out 2. If I plug 1 in, I'll get out 4. -1, I'll get out -4. -2, I will get out -2. So then we can go ahead and plot our vertical asymptote, and we can plot those points. It's my vertical asymptote. I can just draw a straight line vertically through the origin because I can't divide by 0, so I'm never ever going to touch those points. And then I can fill in the points that we've graphed. So we have 1, 4 here, and then 2 is right here. Over on the left, I have -1, -4, and then I have -2, -2. Now, one other thing I do definitely want to fill in before I graph this function is my horizontal asymptote. And that is going to happen with this function at y equals 0. And you can think of that one of two ways. This is in our translated form, so there's technically a +0 constant hanging out on the end. But the other way you can think of it is if you can't plug 0 in, there's no way you can get 0 out of that equation because there's no number I can divide 4 by to get to 0. So I'm also going to have a horizontal asymptote right here at 0. So I'm never ever going to cross this line with my rational function. So it is a good idea to sketch this equation to plug it into your graphing calculator. And your y1 equals, you want to input it like this. And then you can follow the trends of the asymptotes, connecting the points that you've plotted. So you're going to have one branch up this way, and then your other branch is going to follow this asymptote and then come down following the line of the vertical asymptote there. Oops, that one disappeared. So I'm going to have this shape for my rational function. Then after I've graphed, I can identify my domain and range, which are just my possible x values and my possible y values. So those are determined by what our asymptotes tell us. So my domain is that x cannot be 0, and my range is that y cannot be 0. The last thing that's not included on your parts A through C that you would want to be able to do with this graph is identify how it's different from your parent function. So the parent function is 1 over x. So this graph has a vertical stretch, which essentially means that the slope of the graph is steeper than it would be on our parent function 1 over x. So like this area is getting larger faster than we would expect to see with the parent function. Let's go ahead and do another rational graph with number 6. This one has a few different shifts going on, and so we're going to see it translate right or left and also up or down. So you may find it useful to identify your asymptotes when you have the shifts and translations first and then pick your points to graph. So my vertical asymptote here comes from taking a look at this x minus 4. And I know that if I plug 4 into that expression, I'm going to get 0, which means I would try to divide by 0, which is something I can't do. So my vertical asymptote here is going to be x is equal to 4. Then when you have this equation, your HK or translated version of the equation, this plus 3 is going to be your horizontal asymptote. So I can go ahead and sketch in those values. So I have x equals 4, which means I have this vertical asymptote running right through here. And then I have y equals 3, which is right here. And I can sketch this horizontal asymptote there. So I can kind of see that my axis or my center has been shifted. So instead of being centered about the origin, the two branches that we graphed, they're going to be centered about 4, 3. So now I want to pick my points, and I want to pick some that are going to be smaller than my vertical asymptote, and I want to pick some that are going to be bigger. So let's go ahead and fill in a quick XY chart. So x equals 4, that's my vertical asymptote. So I want to pick 2 values above, 2 values below, just to sketch out the shape. So 2 above, we could pick 8 and 6. And then down below, we could pick something like 2 and 0. And it's okay to get decimal approximations for this kind of work. So if I plug in 8, down on the bottom, I would get 4. So I'd have 2 over 4, which is 1/2, plus 3, which would be 3.5.